Okay, this is question 16. Given that for this system of equation, x, y, z are real numbers, it's clear that when x, y, z all equals to 0, it satisfies the equation in the system. So we are asked to find the smallest positive integer p such that the system have more than one set of solutions. So we start from here. So in this case, 3z will equal to negative 6x plus 4y. We will sub in the z inside here. 4xy plus z, and this is 2y plus px equals to 0. All the term times 3, so this is 12xy. And after times 3, this will be negative 6x plus 4y. And 2y plus px equals to 0. 12xy minus 12xy, and it cancels off. Negative 6px squared minus 8y squared and minus 4pxy equals to 0. This is actually a quadratic equation in x. So we will write as x squared, x equals to 0. We will divide each term by negative 2. So this is 3px squared, and for x this is plus 2py, and for non-x it is plus 4y squared. Again, this is a quadratic equation in x, and since x is a real number, the discriminant of the equation will be greater than or equals to 0. The discriminant is b squared minus 4a and c will be greater than or equals to 0. So there will be a 4 cancelled with the 4. So this is p squared y squared. And this will be equal to 12py squared greater than or equals to 0. Okay, so we will take out y squared, we take out p, and this is p minus 12 greater than or equals to 0. Since y squared is always greater than or equals to 0, and this will mean that p minus 12 is greater than or equals to 0. And therefore, p greater than or equals to 0, or p is less than or equals to 0. And because we want to have a positive integer p, so p must be at least a 12. We want to make sure that when p equals to 12, it will fulfill the condition. So we verify here. If p equals to 12, this equation will have exactly one solution. So, and the solution is equals to negative b over 2a. So it's negative b over 2a. And p can be cancelled off. 2 cancel off. This is negative y over 3. So in other words, y equals to negative 3x. So if x is equal to x, y equals to negative 3x, then z from here is negative 1 over 3, 6x plus 4y. 4y is equal to negative 12x, and this will equal to 2x. And we can verify that x, y, z, when it is equal to k, negative 3k, and 2k, will be always the solution for the system for any value of k. So in this case, where p equals to 12, you will have more than one set of solutions. In fact, it has infinite many of solutions. And therefore, the smallest positive integers is equal to 12. 12 will be the answer for question 16.